and linked list cycle. So let me just share my screen. So because of time, I'll engage you guys on the understanding the question part, and then yeah, I'll walk you guys through the approach. So we, just like last time, and this is the basics. So the way we are going to solve this problem is the advisable way to solve interview problems. So we basically use what is known as an umpire method. So that's you and for those who attended the last session. Um, so you and I'll break this down in a minute. Okay, so the U represents understand, the M represents map, the P represents plan, the I represents implement, the R represents review, and the E represents evaluate. So the U just understand the problem. The map is map the problem to an approach or a data structure or whatever kind of method you can use to solve it. The P is to plan, you plan to solve. So after you've mapped, then you can write some pseudocode, just plan how you're going to write the code. Then the implement part is simply translating the planning phase or the pseudocode into actual code. And then the R is to review and check your code for errors and the likes. Then the E is to evaluate. So evaluate the time complexity, evaluate the space complexity, and the general efficiency of your code. So we can understand the question together. Just do that. Our question says, given head, the head of a linked list, determine if the linked list has a cycle in it. There's a cycle in the linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS is used to denote the index of the node that tail's next pointer is connected to. Note that POS is not passed as a parameter. Return true if there is a cycle in the linked list. So basically, from this example here, they are saying we are given a linked list, just like Tao explained it, and it's like a circular linked list from what Tao explained. So when you go to the end of the linked list, instead of it pointing to now, meaning that the list is over, what it does is that it goes and points at another number before it goes and points at another number in the linked list. So meaning that linked list doesn't end because it's continuous. And okay, before we that's the explanation I'll give. So let's do some clarifying questions. What are some clarifying questions that you guys might have?
Sorry, concerning what?
Some clarifying questions for this question, like what are some clarifying questions that you guys would have based on this question that we have been given?
We have an empty linked list, something like that.
Okay, can we have an empty list? Okay, that's one. Any other questions, clarifying questions? We also agree on inputs, right? Our input is a linked list. We agree on inputs and outputs.
Yeah.
And then our output is a what? Is a Boolean, right?
Yeah, Boolean true, of course.
Boolean, okay. Any other clarifying questions that you might have? So to answer the first clarifying question, the number of nodes in the list is in the range 0 to 10 to the power 4. So yes, we can have an empty linked list.
Okay.
Those are the inputs. So are those all the clarifying questions? So do we all understand the question before I move forward?
Yes, I do.
Okay. We got John Toluwani and Tia. I hope I'm saying
Yeah,
your name right. Is
so
it
can you hear me?
Tia or Tia?
It's Tia, and yes, I understand the question.
Okay, Tia. Okay, you understand the question. Okay, great. So, sorry, I'll just do some whiteboarding here, right? So then we have, okay, we're done with our understanding phase, and then we can move to the matching phase. So what are we going to use to solve this problem? What data structure are we going to use to solve this problem? And what kinds of methods are we going to, are any algorithms, data structure, built-in data structure, what are we going to use? So of course the question, I'll add one. Of course the question is a linked list question, so we are using linked lists. Anything else?
I think, yeah, we want to iterate through the linked list. So we need to have like an
Okay.
iterator or something that goes through the linked list.
Some form of pointers, right?
Yeah.
Okay. And then I also suggest we use Floyd's, tortoise, and hare algorithm. And I'll explain this in a minute. So, okay. Since that's all, so I want you guys. So in a normal linked list, so we are checking if a linked list has a cycle. And first, I want us to think about it. Let's stop thinking about code for a minute. Let's just think about it practically, right? In a normal linked list, it's like, and I'll explain this using Floyd's tortoise and hare algorithm. In a normal linked, okay, sorry, let me do this. In a normal linked list, imagine this is a racetrack, right? And the race starts here, right? So we have a tortoise here, right? And we have a hare. Okay, first, before we think about the tortoise and the hare, in a normal linked list, a normal linked list is like a racetrack where the race, if the race starts here, right? And the race ends here. When we start running, we'll just go like that, right? Like the race is going to it's definite that the race is going to start and end. But when the linked list is a cycle like this, so we have a circular racetrack, that simply means that if our starting point is here, right, and our endpoint is here, or sorry, our endpoint is going to be our starting point, right, in a circular racetrack. So in that circular racetrack, our starting point and our finishing line is here. So in a circular linked list, we are simply saying that we are going to run through this linked list infinite times, right? Do you guys agree?
Yeah.
If we have, it's a race and we have infinite rounds, we're going to run through this infinite
Well,
times. So,
I have a question concerning that.
okay.
So based on the example, first example we looked at and what you said earlier, it's not exactly that we're going to come to the starting point. Like we're not going to come exactly to this. It might be the starting point. Sometimes from the tail, we might not exactly go to the starting point.
Yeah,
That means like
sometimes you may,
we just end, like we could just come back. If we just come back to any previous node, let's say it was even the previous node before the tail, would that still be a
oh yeah,
cycle?
don't think about it in terms of code for now. Yeah, don't think about it in terms of code for now.
But yeah,
I
do
just
you get the
wanted to,
question?
okay, sorry, I don't think I'm getting your question.
Did you get the question? Like I was saying, like the way you do the circle, like the circular field, I'm saying since we don't actually come back to the starting point all the time, we just return to any parts that we've seen before in the, let's say, in the race.
Okay,
So,
okay, yeah.
So just trying to point that out.
Okay, yeah, I get your point. I think it's more of like a point than a question, right?
Yeah, it's like a question, like just trying to say that, like, how do we address that case in that scenario, something like that.
Or if we've seen that before?
Yeah, like if we don't exactly go to the starting point, addressing that.
Okay, I get what you mean. So, okay, we'll address that. I think we'll address that in the explanation.
Okay.
I think it will get clear as we go. So, just like I said, so we know the famous tortoise hare story, where we had the tortoise and the hare, and the tortoise was moving slow. So in this case, if this is the hare, let me write the hare in red. If this is the hare, okay, let me start with the tortoise, which will be in black. This is the tortoise. We're going to say the tortoise moves. For every one step that the tortoise makes, the hare moves 2 steps, right? So moves 2 steps because the hare is 2 times faster than the tortoise, right? This is a normal linked list. So when the tortoise moves again, the hare is going to move 2 steps. When this tortoise moves again, this hare moves 2 steps and it finishes the race. So when when one of these finishes the race, we can simply say that race is over because the tortoise won, the hare won. But then in a case where we have a cycle in the linked list, what's going to happen is we're going to have a racetrack like this. We're going to have a circular racetrack. I'm sorry for making it so big. Just want to get the point across. So if the tortoise starts and it makes 1 step, I'll make the steps large so we can finish quick. We'll say, okay, let's give this race a number of rounds. Let's say it's a 5-round race. And the hare starts, so the hare makes 2 steps. Because it's 2 times faster. Remember, the hare is 2 times faster than the tortoise. The tortoise moves, the hare makes 2 steps. The tortoise makes 1 step, and the hare makes 2. The tortoise makes 1 step, and the hare makes 2. The tortoise makes 1 step, and this hare makes 2. This tortoise makes 1 step. Sorry for the overlapping thing. The hare is here. Let me use red now. This hare makes 2. 1, 2. And the tortoise makes 1 step, and the hare makes 2. And this tortoise makes 1 step. This hare makes 2. So it's quite a long race. Sorry for the long race. The tortoise makes 1 step. The hare makes 2. We are dragging. Sorry for the dragging. It makes 2. 1 step makes 2. Seen the pattern? Hope I've seen the pattern. Then makes 1 step, right? Then the hare makes 2. So at a certain point, it's going to catch up with the tortoise and overtake it for a second time, right? So the moment they meet, if they meet again, then we can know that there's a cycle because that means how can I say this? In this case, the finishing line is like the now pointer at the end, right? That means they didn't find an end. They found another route around. So it's like they started from the same point, they started moving at different paces. The slow one was behind. The fast one was moving 2 times faster, but then the slow one was still moving and it caught up again. So now let's put that into linked list context. And I hope I'm not spending too much time explaining so that we can start coding. Let's put that into linked list context. If we have a linked list, say 1, 2, 3, 4, and then we have a cycle, right? Comes here. If we have a slow pointer, and this one is the head, right? And both of them start at 1. So slow starts here. Slow and fast starts here. So slow moves once, and slow is here, right? So I want to write like this. Apologies. So slow will be here. Fast will be here, right? Because fast is moving 2 times. 2 times the speed of slow. Slow will be here. And then fast. Sorry. And then fast will move here. Fast will move here. And then because the cycle is connecting it to this point, fast is going to come back to this point, right? So I'll just erase this so that it's not confusing. So now fast will be back here. And then slow will be here. And then fast, so when slow moves here, fast is going to come back here. And so because they met again, so they were together at first, and they met again, that means you have a cycle in the linked list. But in a case like what I showed for the first race, fast is going to finish and they won't meet again. So if in a case where they finish and they don't meet again, that means you don't have a cycle in the linked list. So John, have I answered your question in like explaining?
Yeah.
Okay, great. So to plan, we're going to say, we're going to have 2 pointers, a fast pointer and a slow pointer. And they're pointing and they'll point at the head. And then when we initialize the 2 pointers, we're going to have the while loop that continues as long as our first pointer is not pointing at now, as long as the element it's at is not now, as long as fast is not now, and fast.next is not now. So as long as the element that fast is pointing at is not now, and the element after it is not now, the while loop is going to continue iterating, right? And then just like I said, we're going to make slow move once. So we're going to make the tortoise move once. Slow is the tortoise in this case. And make fast move twice for each iteration, right? And then at the end of the day, we want to check if at any point fast equals to slow, then we want to return true. If that loop is done and it keeps going and they don't meet at any point, then we are going to return false, right? So is that approach clear for everyone? Is there anyone with like questions?
So, sorry. Can you
Okay.
on that plan, right? On that plan, the second point, while loop that continues as long as fast and fast the next is not known.
Yeah.
Are you saying that? Are you saying that because would you just briefly, like 10 seconds, just speak on that a bit?
Okay, sure. So let's think of it like this. A linked list, that's not a cycle, right? forget about slow for now, because fast is going to be quicker than slow. So that loop is simply checking, well, fast is not now, so this is not now, right? And this dot next is not now. So if this and this dot next is not now, then move fast. So we are checking, say, fast is going to move. So fast to be here, then it's going to eventually it's going to be here, right? So, and then again, we check, well, fast and fast dot next. So is it now? No. Is the next now? No. So let it move. And then when it moves, what has happened now? It has come out to, what has happened now? This pointer is now, right? This pointer is pointing at now.
Yeah.
So because this is now pointing at now, our loop can stop executing. Does that make sense?
Yeah, it makes sense. So how does the slow now play into that?
Okay, the slow plays into that because the fast is quick. The fast is moving quicker than it, right? So fast is simply checking the conditions for I hope I'm explaining this right. But fast is simply checking the conditions for slow. So fast has checked if fast and fast the next it has moved. So it's giving slow the leeway, say, because there's numbers in front you can move. So slow can move here. And then it checks again, fast done now, fast done next, it moves, right? So when it moves here, then it's telling slow, you can move. But then when it checks this condition for another time, when it checks this condition the next time, it finds that it's at now, so slow can't move. So that ends the what's this. So to bring it into context for a linked list that has a cycle, say our cycle is coming back. Sorry, I'm sorry for my bad drawings. I'm not used to like whiteboarding and the likes. But say, so, okay, I can write on my screen. So say, oh, yeah. So say, so it checks fast, the next is not none. So it moves here, and then it tells slow, you can move, okay. And then it checks fast, the next is not now. Fast and fast the next is not now, okay, fast you can move. So fast moves, and fast is now back here, right? Because of that cycle, that brings it back. Because 4 is pointing at that. Then tells slow, okay, slow you can move. So now slow moves, and slow is at 3, right? And then it says, okay, fast and fast the next is not now, okay, fast you can move. So fast can move. And then it tells slow, okay, slow you can move. So slow moves, but then at this point, in that same loop, we are checking the condition if fast is equal to slow. So the fast and fast the next is just simply trying to say like keep moving. And the reason why we are saying while fast and fast the next is because fast is moving at a quicker rate than slow. So it's checking the way for slow. Does that make sense? I hope I'm like explaining it right.
Okay, so just to summarize quickly, so it said return true if a cycle is found. So a cycle means that fast will be equal
Fast
to
and slow have met again, yeah.
so that's when the code will end more or less, right?
Yes, that's when that's when it will end.
Thank you.
Okay, great. So we can implement. I'll implement outside that. So we'll just follow our pseudocode here. We're saying 2 pointers, fast is equal to head, okay? And slow is equal to head. They're both pointing at the head. And then we are saying, wow, fast and fast dot next. Or to break this down, I'll say, wow, fast is not none, or wow, fast is not now. And fast dot next is not none, right? So we are making slow move once. So slow is going to be equal to slow dot next, right? And fast is going to be equal to fast dot next, because it's moving twice, dot next, right? And then in this same loop, we check if at any point we've made them move and fast is equal to slow, we return true. Also, if we come out of this and that condition is not met, you can just say return false. Yeah. So if at all this condition is met at any point that the fast becomes equal to slow, then we can return true. Then also, let me just teach you guys a trick. If you ever try to find the middle of a linked list, you can use this same algorithm. Do you remember when I was explaining the fast and fast the next thing for a thing that has a null pointer? If they start at the same point, fast and slow, fast moves, it's here. Slow is here, sorry. Slow is here. Fast moves again, fast is at now, right? Fast is at now. Then slow moves once. The moment fast becomes now, slow is always in the middle of the linked list. That's just a trick that you guys can learn. So if you ever ask that in an interview, just implement the same algorithm. Just say, well, fast and fast dot next, slow is equal to slow dot next, fast is equal to fast dot next, then return slow. When you return slow, you're always returning the middle of a linked list. So that's just a trick. But yeah, so that's our code. So we can review the code. Does our code look correct? Let me hear from you guys.
I think based on your explanation, it looks good.
Okay, so we can, so then we can evaluate the code. So what will the time complexity of our code be? What do you guys think?
What is the is there any specified thing we have to like follow for this question?
Any specified what?
Like time or space like then is like do you have a time or
No, we've only been asked to solve it in all of one space, not time, but for space, as you can see on the left, we've been asked to solve it in all one space. So yeah, but for time complexity, it's up to you, but it's always good to have to have it as optimal as you can. So according to you guys' analysis, what is the time complexity?
time?
Hello, time, yeah.
Go ahead, you want to say something?
What's the time complexity?
People wanted to talk.
No, I was just asking him to confirm. No, I don't have anything to say.
Okay, I was meaning like for time complexity, looking at this approach, because we are using fast and slow, that means in the worst case, because time complexity look at the worst case scenario. So what happened in the
Okay.
worst case scenario? So in the worst case scenario, we don't have a cycle linked list and we have to visit every single node in the linked list. And that will take us O of n time because we perform n operation of moving through the entire
Through
linked
the entire
list.
linked list. Okay.
So I would say the time complexity should be O of n time complexity.
O of n. Okay. Yeah, I agree. Yeah. And what was space complexity be? Space. Hello, what's our space complexity?
I think Taya is saying something. We can't hear you very well. Are you trying to say something, Taya?
Hello, Tia, were you trying to say something?
Oh,
Oh,
maybe she
maybe
has some
she
issue.
logged out.
Yeah, she has some
Okay.
network issues. Okay.
Okay, so I think our space complexity is O of 1 because we didn't create any extra space. We performed the operation within the linked list, right?
Yeah.
Yeah, so our space complexity is O of 1.
What about fast and
So,
slow?
sorry? No, those are just pointers.
Sorry?
Those are just pointers. They don't like hold any, they don't hold, how can I say this?
Yeah,
They are
they're
not
constant space. Yeah, they're just variables. They are constant. We use them. They take constant space. The time complexity is O of n. Yeah, Tia was asking the time complexity. You could just speak about that again this way.
Okay. So the time complexity is O of n because at the worst case, we don't have a cycle in the linked list. So we are visiting every single node in the list. But yeah, so our time complexity is O of n. Because at the worst case, we are visiting every single node in the linked list. And then we said our space complexity is O of 1 because we are not using any extra space. We are just doing the operation within the linked list that we have been given itself. Yeah, is that clear?
So sorry. So when this constant space, it doesn't count, but once it's changing, it counts.
Sorry, I don't really understand your question.
For the space stuff, I asked for about fast and slow because it said O of 1 for the space that it doesn't. We're not using we're not making any new something. So it's
Yeah.
so. Could you explain that, please?
Okay, so the reason why fast and slow are not creating any extra space, right, is because we are so constant, like we are making them point at something in the list that already exists. I don't know if my explanation is the best, but yeah, we're making them point at an element, sorry, we're making them point at like an entity of the linked list. And then it's not like they are creating any new variables from what we have already been given. We are just using them to check and run through the list. Maybe John can give a better explanation for that.
Which one? The space
The
complexity?
space complex for fast and
Yeah.
slow. How fast and slow?
So fast and slow are just pointers. Basically, they take constant space.
Oh,
So we
let me
don't
just run
count.
the code because
We don't
the
count
session is almost
constant
done.
space. Yeah, we don't count constant space in the time and space complexity. So you must know that we don't count the time and space like what's it called? The constant space when we're analyzing the time and space complexity. So it's constant like O of 1. But then let's say we created
Yeah,
a new linked list and we're iterating through the new linked list we created. We made a copy of the original linked list. And that means we are
yeah,
using O of n space
more than
because we
space.
created an exactly like a new linked list. We created a new linked list. So that's the reason.
Yeah.
So our breakout is
Okay.
ending now. Yeah, and
Yes. So
thank
our
you guys.
solution passes you guys